My name is Jungbin Mok. These are my courses. The title of my presentation is Stratospheric NO2 Profile Climatology for OMPS LP. So at first, I want to show why we need NO2 climatology. This figure shows ozone cross-sections and NO2 cross-section as red and blue color respectively. As you can see, NO2 cross-section is become larger than ozone cross-section at 306 nanometer. However, NO2 cross-section, NO2 concentration is much smaller than ozone concentration. So it does not affect the radiance calculation much. So for this, I plotted ozone and NO2 absorption optical depths defined as number density multiplied by absorption cross-sections. As you can see, at shorter UV wavelengths, NO2 absorption optical depth is not significant, but it's increased as the wavelengths increase, as this figure shows. Also, I plot the ratio NO2 optical depth divided by ozone optical depth. Here you can see the upper axis. And especially at 353 nanometer, you can see the ratio is increasing as 2.5 at 30 kilometer. That is very significant compared to ozone optical depths. So especially 353 at 20 and 40 kilometer, we use the altitude registration. So it is important to consider regional NO2 profiles as a climatology. This cartoon shows how we construct NO2 climatology. We use GMI NO2 profiles. You can at first because other missions or measurement cannot provide any measurement at 1:30 p.m., which is the OMPS LP overpass time. So at first we collocate between OMPS and GMI, and then we create monthly files, and GMI provide the volume mixing ratio, so we convert into the number density. So the final, the generated GMI NO2 climatology as a function of 12 months and 36 latitude beams and 90 solar zinc angles and 81 altitude levels. Especially for solar zinc angle, we provide in AM and PM due to large diurnal variation of NO2. However, the most of solar zinc angle beams are empty because our collocation is based on the OMPS polar orbit, local time, and solar zinc angle. So the GMI NO2 profile we use as a climatology to create climatology is validated by Strode et al. 2022. As you can see in the left panel, it's comparison between GMI and SAGE-3. You can see GMI simulation underestimate NO2 peak near the peak around 30 kilometer, like this one, and compared to SAGE-3. And also GMI as red shows place lower than SAGE-3 measurement, especially in southern hemisphere, like this arrow shows. And also they compare the OSIRIS, and GMI simulation shows a bias high compared to OSIRIS version 6.0 from 10 to 40 kilometer. But this low bias in the low bias in the SAGE is not appeared in the OSIRIS comparisons. We use OSIRIS version 7.2 measurement because it provides NO2 profile shifted to local solar noon using this ratio. This ratio is calculated from the photochemical model, like right figure shows. Mostly these reference from the Dubé et al. 2022, 2020, and 2021. You can see the NO2 diurnal variation is very rapid, especially sunrise and sunset. Also, thanks to the model simulation, they measured NO2 near sunrise and then converted into the NO2 at 12 p.m. So we can compare using this NO2 profiles. This is a comparison between GMI and OSIRIS NO2. We use a 10-degree monthly journal mean in July 2017. Left panel shows OSIRIS and GMI as a black and red color. And horizontal bar is here. You can see it's 1 standard deviations. As you can see, it shows a general agreement within 1 sigma standard deviations. If you look at the right panel, it's percentage in difference. From 15 to 32 kilometer, GMI shows overestimation, but outside this range, GMI shows underestimation, especially for upper and lower altitude. And look at the different latitude beams, like mid-latitude and higher latitude. It shows very similar features previous ones. So, and also the profiles and percentage difference shows very similar with tropical regions. We also compare the old NO2 climatology with GMI during June, July, August from 2014, 2018. You can see the blue, black, red shows the Platmo climatology. It's the old climatology we use, and OSIRIS and GMI. You can see overall OSIRIS GMI shows very similar profiles like this region. And however, Platmo shows significantly underestimate below 30 kilometer, as you can see. We compare old climatology with GMI stratospheric column NO2. Stratospheric column NO2 is calculated from 12 to 45 kilometer. We plotted stratospheric column NO2 as a function of latitude. As you can see, the blue, black, red shows Platmo, OSIRIS, and GMI. The overall, GMI and OSIRIS shows very similar latitudinal patterns, and all over the seasons, GMI and OSIRIS shows very similar features. However, Platmo climatology shows is underestimated by a factor of 2, like this season, I mean JA, and this seasons during winter time, and these regions. And also on SON, you can see the very underestimated features of Platmo. We performed the statistical calculation to compare OSIRIS and GMI stratospheric NO2. The bias and standard deviation in percent is calculated using these equations. R and N is correlation coefficient and number of data. ONG and OMP in the table means statistic between OSIRIS and GMI, and statistic between OSIRIS and Platmo. And based on the bias comparison, you can see GMI shows little overestimation like this. And however, Platmo shows significantly underestimate. So in other words, that means GMI shows less bias compared to Platmo. And if you look at the standard deviation in percent, GMI shows less average percentage standard deviation than Platmo. Switching gears, we try to apply the machine learning technique to derive NO2 profiles from OMS LP observations. NO2 algorithm, classical NO2 algorithm has some difficulty to retrieve NO2 profile because poor spectral resolutions. As you can see, this plot, black line shows high spectral fit NO2 absorption cross sections. But if we apply the bandpass, cell-like bandpass, you can see the very limited information like this smoothing curve. So we advances in machine learning technique will improve these issues, and we expect better accuracy of NO2 profiles. For this, we use 61 triplets, and the reference of wavelengths for triplet is 377 and 500, like this arrow shows. And for machine learning approach, we performed the sensitivity study. As you can see, we try to increase GMI NO2 by 10% to see how residual change. Residual means the difference between measured and calculated radiance. So as you can see, 10% change in NO2 profile produces only 0.5 changes in radiance. So we try to look at how different is without triplet and with triplet. You can see if we apply the with triplet, you can see the lower values of residuals compared to without triplets. So that means triplet formulations and altitude normalizations it can be used to reduce sensitivity and also cancel out the signal from aerosols and clouds. So machine learning training, we use calculated radiance and with triplet and altitude normalizations, and we use retrieval for using LP measured radiance in triplet and altitude normalizations. More details, you can see the Michael's presentation tomorrow. This is a comparison between machine learning and OSIRIS NO2. You can see machine learning shows very similar features like we saw before between GMI and OSIRIS comparisons. This is a not surprising result because the features and quality is translated into the in the training is translated into the machine learning estimations. However, as you can see, the bias is decreased from 20 and 30 kilometer. Finally, we compare with machine learning and OSIRIS stratospheric NO2. As you can see, GMI and OSIRIS in machine learning here, and especially summer and fall and winter time, you can see machine learning stratospheric column is slightly overestimated than OSIRIS. However, as you can see, interestingly, the machine learning and OSIRIS is very similar during the springtime. So our goal is to enhance the climatology of OMPS LP by using GMI NO2 profiles. GMI NO2 profile shows a good agreement with OSIRIS compared to our old NO2 climatology. GMI consistently overestimate NO2 concentration between 15 to 32 kilometer compared to OSIRIS. But GMI shows good agreement in terms of latitudinal and seasonal variations. To retrieve the NO2 profiles, we use a machine learning technique, and it shows a reasonable agreement between OSIRIS and GMI. Thank you.